Hello again. So let's see, what we ended on in the previous section was we set a polynomial f of x equal to 0 and we were trying to solve for x. But we kind of had a hint. They said, okay, here's a number and it is a 0. Now go find all the solutions. So the first 0 we used to do synthetic division, and then we were able to break the function down, or the polynomial down, into all its smallest pieces to solve it. So that's kind of bringing us to what we're trying to do in this section. In this section, what we're trying to do is take a polynomial and figure out all its solutions, which will correspond to the x-intercepts of the graph. So we want to find all the x-intercepts. In the very last examples in the previous section, we were given one of the solutions. They said, here, this guy's a 0, now go find all the other ones. In this section, though, we're going to find out what do you do if you're not given any zeros. Like, where do you start, if you have no idea what any zeros are. So that's what this thing, the rational zeros theorem, is all about here. The rational zeros theorem. Okay, what does it say? It's kind of hard to wrap your mind around at first, but I think you see it maybe 2-3 times and you'll say, oh, okay, I kind of get the hang of it. It's kind of weird, but whatever. So, okay, it says, let p of x, which is a sub n, x to the n, plus a sub n minus 1, x to the n minus 1. This is just a very general way to write a polynomial. So don't worry about this guy. Just think of the polynomials we've seen before. Picture those guys. So let that be a polynomial where all the coefficients are integers. So that's part of the definition of a polynomial. We don't want anything that's not an integer to be a coefficient. And then consider a rational number denoted p over q. So basically, rational number is a fraction, just so it doesn't sound like jargon. This is a fraction. Okay, consider a rational number or a fraction p over q, where p and q are relatively prime. That just means they have no common factor besides -1 and 1. Okay, so pretty much that just means that p over q is not reducible. It's already reduced to its lowest form. So it says if p over q is a 0 of p of x, then p is a factor of a sub 0, which is the constant term. Let me see, I'm going to write that down here so we kind of have it. P is a factor of a sub 0, that's the constant term of the polynomial. And q is a factor, I'm going to write term, okay. Q is a factor of a sub n, which is the leading coefficient. Alright, so that just kind of sounds like a fact about any zeros. Like, okay, whatever, any zeros, if they're fractions, they look like this, and it has to divide this. But really what that helps us with is it narrows down the field, because if you give me a polynomial, I have no idea what the zeros are. Honestly, what I have to do is just guess. I'm going to guess, let's say 1. Is that a 0? Maybe, maybe not. Is -1 a 0? I don't know. But this is going to narrow it down. So instead of me guessing and stabbing in the dark, I have at least a little bit of a guideline as to what to guess and what not to guess. Let's try to just use that idea. It's so weird. We're going to try to use that to list all the possible rational zeros of f of x equals, let's see, 4x to the 5th plus 12x to the 4th minus x minus 3. So in this example, we're just kind of getting used to this rational zeros theorem. They don't actually want us to find all the zeros. They just want us to find all the possible ones. So let's see, as the rational zeros theorem says, if I have a 0, it's called, let's say, p over q. Here's a rational 0, aka a fraction. Rational 0. Then p, what does it say? P must divide, it says here, a sub 0, which is the constant term. The constant, -3 in this one. And then q must divide the leading coefficient, which is 4. Leading coefficient. That's pretty much what the rational zeros theorem says. So okay, we're gonna kind of simplify that a little bit. Let me kind of color code here. We said that p must divide into -3. So I think about what are all the factors of -3. So the factors of -3 are 1 and -1. So that's a possibility, because those both divide into -3, but also 3 and -3 divide into -3. So that means that p could be any of those 4. P is basically, that's pretty much what we're saying here. P could be 1, -1, 3, or -3. But that really narrows it down. P, the numerator of any 0 of this polynomial, must be one of those 4 things. And then similarly, we can do something for q like that. Because here we said q must divide into the leading coefficient, which is 4. So then we think about, well, what are all the factors of 4, or all the things that divide into 4? Well, 1 and -1 divide into 4. So do 2 and -2. And then 4 and -4 also. Those divide into 4. So pretty much what we're saying there is Q could be any of those guys. It could be 1, it could be -1, it could be 2, -2, 4, oh, what the heck, 2, 4, and -4. All right, so then what we're going to do is figure out what are all the possible combinations of P over Q, is what they're writing here. But we can write it maybe in a more, I don't know, spelled out way. P over Q, all combinations. I'll say all combos just to make it short. So I'm just going to think about any of those P's. Let's see, P, I'm going to highlight it. P could be 1, -1, 3, or -3. And then Q could be, what was the other guy? 1, -1, 2, -2, 4, -4. One of those. So I just think about all possible combinations of P's over Q's. So, first of all, let me just fix P. Let's say P is 1. Okay, let's just say P equals 1. And then what could Q be? Q could be 1 from the highlighted purple. Q could be -1, so it's 1 over -1. P is 1 right now. I'm just saying P is 1 for now. And Q is ranging. So Q could be 1, it could be -1, it could be 2, it could be -2, it could be 4, it could be -4. Oops, -4. So that's all the possible things that can happen when P is +1. What about when P was -1? Let's see, P could be -1, so it could be -1 over, the first possibility for Q is +1. Could be -1 over -1, because that's another possibility for Q. Could be -1 for P over +2 for Q, -1 over -2, -1 over 4, -1 over -4. So right now, like I said, what I'm doing is just listing all possible combinations of any of those green numbers over any of those purple numbers, or yellow, or pink, whatever the hell. P could also be 3. All right, what about when P is 3, what do we get? 3 over 1, because that's a possible value of Q. 3 over -1, 3 over 2, 3 over -2, 3 over 4, and 3 over -4. Oops. And then lastly, P could be -3, and I'm now going to let Q range over those same numbers in the denominator. -3 over 1, -3 over -1, -3 over 2, -3 over -2, -3 over 4, -3 over -4. So this is a lot of possibilities, but I think a lot of these are repeats. So let me see. I'm going to kind of try to keep track here. I got the very first one I wrote was 1 over 1. That's just a 1. I'm just trying to clean everything up and simplify that. So P over Q, it could be any of these guys. I got 1 so far. Done with that. Here I got 1 over -1. That's just -1. Okay, so that's another possibility. What else? 1/2, -1/2, 1/4, -1/4. I'm going to write all those guys down. 1/2, -1/2, 1/4, -1/4. Okay. In my next row, I actually have all the same guys. Notice, -1 over 1, that's just -1. And I've already listed that. That's already a possibility. The next one is -1 divided by -1, which is +1, but I already have that in my list. So moving on, -1/2, I already have that. -1 over -2 is +1/2, I already have that. -1/4, I already wrote that. This is +1/4. So I already had all those guys. This was kind of just a waste of time, that second row. Let me see if I get any new ones out of the third row. 3 over 1 is a 3. And then 3 over -1, that's -3. That's a new guy. 3 over 2, I don't have that yet, do I? No. -3 over 2, I don't have that either. And then 3 over 4, -3 over 4. I don't have those either. -3 over 4. Okay. So these are so far all the possibilities. And notice, though, that the very last row also is another bunch of repeats. -3 over 1 is -3. I already have that in my list. -3 over -1 is +3. I already have that. I have this guy. I have this guy. I have this guy. I have this guy. So our answer is just the very bottom row here. This is all the possible values of P over all the possible values of Q. Ugh, that seems like a lot of work, but I think the next example we do will try to make it easier and quicker. This one was, this one was tough because it was our very first one that we've done. But let's try that again with this next one here. We got a new polynomial here. 3x to the 4th minus 11x to the 3rd minus x squared plus 19x plus 6. So let's see, we're going to say if P over Q is a rational 0, is a 0, if that's true, then P must divide into what the rational zeros theorem says, it must divide into the constant term 6. constant term. Okay, maybe I'll kind of color code these guys. Q, the denominator, must divide into the leading coefficient, which is 3. Leading coefficient, okay. And then let me kind of break that down. Let me think about all the possibilities there. For P, first of all, P divides into 6. Let me think about what are all the things that divide into 6. P must be, let's see, 1 and -1 divide into 6. 2 and -2 also divide into 6. 3 and -3. 6 and -6. So those are all the possibilities for the numerator P. Q has to divide into 3, which means there's fewer options for Q. The only things that divide into 3 are 1 and -1, 3 and -3. So those are our options right there. Now I think of all the possible combinations of those P's over those Q's. All combos. But I think unlike in the previous one we did, now that we're kind of more well versed in this, I think I can leave the plus or minuses as they are. I'm not going to separate a 1 and a -1. I'm just going to leave it as plus or minus. So let's say one combination would be this guy, plus or minus 1 over plus or minus 1. Because remember, it's supposed to be P over Q. Another thing would be maybe plus or minus 2 over plus or minus 1. So I'm letting Q be the same guy, plus or minus 1, but P being 2, or plus or minus 2. Now let's try plus or minus 3 over plus or minus 1. And then plus or minus 6 for P, but leaving Q as plus or minus 1. And then I can do the exact same thing, but now let's say Q is plus or minus 3. So I have all the same numerators, it's just now the denominator is plus or minus 3, instead of plus or minus 1. Minus 3, plus or minus 3. 6 over plus or minus 3. There we go. I think that's all the possible combinations of any of those red numbers in this box over any of those blue numbers. And now I'm just going to look at each of those separately and try to simplify. And I think that'll be my final answer. P over Q is one of the following. Let's see. If I put plus or minus 1 over plus or minus 1, think about any possibility where the numerator is negative, the denominator is positive, both are negative, both are positive. I think all I'm going to get out of that is 1 or -1. That's it. There's nothing else that can happen there. The next fraction I have is plus or minus 2 over plus or minus 1. The only thing that can happen out of that is a 2 or a -2. No matter what I let be positive, what I let be negative. Because if they're both positive, it's positive. If they're both negative, it's still positive. If one of them is negative, one's positive, it's negative. That's all that can really come out. Similarly for the next guy, plus or minus 3 over plus or minus 1, that can only be 3 or -3. And the very last one in that row, 6 or -6, is all that you can get out of that. Then we'll look at the next possibility. Plus or minus 1 over plus or minus 3, all you're going to get is 1/3 or -1/3 out of that guy. And then same thing with the next guy. You got 2/3 or -2/3 is coming out of the next one. The next one, however, think about that guy. Plus or minus 3 over plus or minus 3, that's either going to be a 1 or a -1. So that one actually gave me nothing new. That was kind of a waste of time, that guy. Does that make sense? Yeah, because that could either be 3 over 3, -3 over -3, -3 over +3, or +3 over -3. Either way, that's only a 1 or a -1, which we've already listed, so what a waste of time. The same thing with the very last guy. 6 over 3 is 2. And there's only, you're either going to get that or a -2, but I've already listed those here. So these are all our possibilities. That's our answer right there. All those guys in the red box. So I think that time it seemed a little easier. We just kind of streamlined the process a little bit. And then we'll do more of these later, but it's just, the more of these you do, the better you get at it. You kind of get the process down. Okay. So as we said before, the next thing, the reason that we learn the rational zeros theorem is because we want to use it to be able to figure out all the zeros of a polynomial, because what we're working towards is being able to graph these guys. And that'll, because the zeros will represent the x-intercepts. So let's see, this kind of outlines the steps of how to find all the zeros. It's kind of a long process because it involves the rational zeros theorem, which we just saw takes forever. So okay, if you're given a polynomial function, how to use synthetic division to find its zeros. The first thing you want to do is what we just learned, is use the rational zeros theorem to list all the possible rational zeros of the function. Because that'll be kind of the list that you're going to try to take your values out of, it's pretty much you're going to guess. But that way you don't have to guess every number in the known universe. You just have the smaller version. So if I was trying to work on the previous example, where'd it go? Here we go. If I was trying to find all the zeros of this guy, then I wouldn't have to try every number in the known universe. I'd just try one of the ones in this highlighted box, because those are the only possibilities. So okay, let's see, what do they say? I gotta get back to where we were, huh? So the first step, like we said, is write out all the possible zeros using the rational zeros theorem, and then you're going to use synthetic division to evaluate a given possible zero by synthetically dividing the candidate into the polynomial. If the remainder is 0, the candidate is a 0. So pretty much, you're going to use synthetic division by, you're just going to pick one of those rational zeros from step 1. It's up to you. It's not really like one is better than the others. I just guess whichever one you like the best. If you use synthetic division and you end up getting a 0 remainder, you know you did it right. Or you know you found a successful one. But if you got any remainder other than 0, that means that it failed and you found the wrong, or you didn't find the right one. I'm going to try to keep going and try a new one. If the remainder is not 0, discard the candidate. You have to try a new one. So we're going to repeat step 2 using the quotient found from synthetic division. If possible, continue until the quotient is quadratic. So if we've, it's been a while, but since, let's see, if we've forgotten, quadratic means exponent of 2, or I should say degree 2, sorry. Degree 2. Because once, that's the idea, is once it's down to a degree 2, that means I should be able to factor it the old-fashioned way, kind of. Okay, then we're supposed to find the zeros of the quadratic function. Okay. 2 possible methods for solving quadratics are factoring and then using the quadratic formula. So that's the idea, is we're going to use synthetic division to break it down as many times as we need until we get it into a quadratic. And then from there we can either factor it the old-fashioned way or use the quadratic formula. So we have an example here. It's already actually done out for us, so that's nice. We just kind of have to follow along. It's kind of easier to understand if I don't have to really write down stuff. Okay, the first step is we're going to list the possible rational zeros. Remember, it's p over q like we did in the previous example. P has to divide the constant term, -2, and q has to divide the leading term, which is 1. So that's why they kind of wrote it like this. The only thing that divides into -2 is either +1, -1, +2, -2. And then the factors of 1, the only things that divide into 1 are -1 and 1. And then if you think of all the possible ways you can take any of those p's over those q's, all you're going to get is +1, -1, +2, -2. So that's kind of nice in this problem anyway. Those are our only candidates. So then the next step would be use synthetic division to try to find a rational zero from among the list. So these guys, when they did this problem, they tried 2 and they were successful. But if you try, let's see, 1, -1, any of the other ones, you're actually not going to get the right one. So if you tried, let's say, +1, this guy would not be a 0. The remainder would not be a 0. So you wouldn't have gotten the right answer. So maybe we can show what that would have looked like. Let's see. I'm going to say, let's say I try 1. Usually I start with, I'll try 1 or -1. Sometimes it works, sometimes it doesn't. But let's try 1 here. Just, oh, why did I do it like that? That was silly. It's kind of not how we've been doing it lately. Oops. Uh-oh. What am I doing here? Sorry, something's wrong with my computer, but I think it's working now. So okay, we'll set it up. This, like I said, this is just a more realistic version of this example where I'm going to try one of the rational zeros that we found from the first step. 1, for example. I usually start with 1 and -1 because a lot of times they work, it seems like, and then they're kind of nice and easy to work with. But usually that's what I start with. I don't necessarily get the right one on the first try like they did in this example. So let's try 1. I'm going to try to use synthetic division to see if it actually divides in evenly. So like we did before, I'm going to bring the 1 down and then multiply by the guy outside, which is also 1. 1 times 1 would be 1. And then we're going to add those guys together. The one we just wrote and the guy above it. 1 and 1 make 2. Finally, a number other than 1, right? Then I'll multiply that 2 by the guy outside. 2 times 1 is 2. See, if I add that with the guy above it, I'll get -3. -3 times 1 is -3. Okay, and if I add those together, -3 and -2 make -5. So that means the remainder is -5, which means that x equals 1 is not a 0. Remainder is -5, so x equals 1 is not a 0. So I'd just try another one. Usually, like I said, I just go through the list. I tried one that didn't work. I would probably try -1 next. That actually wouldn't work either. And then I would try +2, and it looks like they've shown here that it does work, because they got a 0 remainder. So I got a 0 remainder. So x equals 2, the number that we tried to use synthetic division with, is a 0. So now at this point we found 1, 0. We're kind of where we were at the beginning of the last example. Because remember they said, oh, here's a 0, find the other ones. So we've had to do a little extra work to find the first 0, but now that we found 1, 0, like it says here, let me find the highlighter here. It says, thus 2 is a 0, and that means x minus 2 is a factor. Because remember we said it's a factor if it's x minus that number. And then the first 3 numbers in the bottom row of the synthetic division give the coefficients of the other factor. Okay, we've seen that before. So the 1 here in the synthetic division corresponds to the coefficient of x squared. 3 corresponds to the coefficient of x. And 1 corresponds to the constant term. Remember the 0 below the synthetic division bar just represents the remainder. So that has nothing to do with the other factor. Alright, so with that in mind, that means since x equals 2 is a 0, that means x minus 2 is a factor. That's why we have that guy here. And then the remainder of it, like we talked about just now, comes from the x squared plus 3x plus 1 equals 0. So now what I want to do is solve this. And like it said in the steps, the steps at the top, where are we? So we want to, as it says, continue until the quotient is quadratic. But actually we've got that right now. The quotient, or what the polynomial that remains, is the x squared is the highest power. So since this is quadratic, there's no need to do any more synthetic division or guessing zeros from the list that we have. Now we can just go ahead and start solving by either using factoring or the quadratic formula. So that's usually I do a little attempt in my mind to factor. You know, I say, does this guy factor? In this case, it doesn't. If it did, I'd try. But you know, if you're really against factoring, you're not really a fan, you can always use the quadratic formula. That'll always work. For the quadratic anyway. Quadratic formula. Alright, so it looks like that's what they did. They plugged A equals 1, B equals 3, and C equals 1 into the quadratic formula here. And then they simplified, so they got -3 plus or minus root 5 over 2. But the other 0, x equals 2, was found in the very beginning of this problem, when we successfully found that synthetic division worked with x equals 2. So that one, yeah, that problem was kind of written out for us. Now let's try one where we're kind of on our own. Let's find all the zeros of this new guy. F of x equals x cubed plus 4x squared minus 3x minus 6. Okay, so first things first, step 1 was we're going to use that the rational zeros theorem to try to list out all the possible rational zeros. Zeros theorem. Okay, so what we did before, it says if p over q is a 0, that means that p divides, or is a factor of, whichever way you want to think of it, divides into that constant term, -6. So what numbers divide into -6? Let's see, 1 and -1, 2 and -2, 3 and -3, and 6 and -6. Okay, and then the denominator q must divide into the leading coefficient, which actually is 1, because the highest powered term is x cubed, and his coefficient is 1. So not much divides into 1, only 1 and -1. Now I'm supposed to look at all possible combinations. Let's see, all possible combinations of p over q. So any of these p's that I wrote here over this q. So I'll do, okay, plus or minus 1 over plus or minus 1, plus or minus 2 over plus or minus 1, plus or minus 3 over plus or minus 1, and plus or minus 6 over plus or minus 1. Now we'll simplify that. Let's see. P over Q is one of the following. So this x equals plus or minus 1 over plus or minus 1. That guy, if you let the pluses or minuses be negatives or positives or whatever, all you're really going to get out of that is a 1 or a -1, no matter what. So that kind of takes care of that. Similarly with the next guy, 2 plus or minus 2 over plus or minus 1 can only be 2 or negative 2. Plus or minus 3 over plus or minus 1 can only be 3 or negative 3. And plus or minus 6 over plus or minus 1 can only be 6 or negative 6. So alright, this is the final result of the rational zeros theorem. This is what we want. So pretty much this is our list of candidates that we're going to guess from to do synthetic division until we get a zero remainder. That's the idea. So that's, at this point, yeah, my idea is to use synthetic division with, I should say, with one of these numbers until I get a zero remainder. Then I know I found a good one. I don't know, if you have kind of a good feeling about one of them, like, oh man, you know what, so for some reason positive 2 is jumping out at me. Well, of course you can always jump to that. But I always try just 1 and then negative 1. I go in order. I'm boring like that. I'm going to try 1. And of course you're dividing it into the polynomial given. So it's x cubed plus 4x squared minus 3x minus 6. So I got 1. Oh my god, I just said it and I already forgot. The coefficients are 1, 4, negative 3, negative 6. Okay. So okay, we'll go for the synthetic division. I'm going to bring the 1 down. Multiply. 1 times 1 is 1. I'll add those together. 4 and 1 makes 5. Multiply. 1 times 5 is 5. If I add those together, I get 2. 2 times 1 is 2. And if I add these guys together, I get negative 4, which is obviously not 0. That means that 1 failed. Now I'll try a different one. Maybe I'll try negative 1. So I'll do the exact same thing, but as if there was a negative 1 in the division box instead of a positive 1. So we'll go do the same thing. Bring down the 1. Multiply it by the negative 1 outside. 1 times negative 1 is negative 1. If I add that with the 4 above it, I'll get 3. 3 times negative 1 is negative 3. If I add those guys together, I get negative 6. And look at that. Negative 6 times negative 1. If I multiply those, I get positive 6. 6 plus the guy above it makes 0. Alright, I got a 0 remainder. That means x equals negative 1 is a 0. Yay! And of course you don't have to write yay on your test. That's not a requirement. X equals negative 1 is a 0. That means that the function I was given, I think they called it f of x, I should be able to write it as x minus negative 1, or x plus 1 of course. Because again, the first factor is always going to be x minus the 0 you found, so x minus negative 1. And then the remainder of the polynomial comes from these numbers that are down in your quotient area. So it should go from constant term, negative 6, and then x power, and then x squared power. So 1 is the x squared power, 3 must be the power, or sorry, 1 must be the coefficient on x squared, 3 must be the coefficient on x, and 6 must be the constant term. And now I'm supposed to solve this. Let me see, I'm going to clean this up a little bit. It looks like I'm going to write that as x plus 1, just so I don't confuse myself. I'm going to drop this 1 in front of the x squared, just to make it simpler looking. Alright, and now that the part that remains here is quadratic. This guy is quadratic. That means that I shouldn't have to use synthetic division again. If this was like a higher power, like a third power polynomial, I'd actually have to use synthetic division into that, try to break that down further. So if it was a third power, let's say, I would use synthetic division until I found another candidate that actually gave me a 0 remainder. That would break the cubic, or the third power, into a linear x minus whatever times a quadratic. So it's like kind of like let's see, the original power on your polynomial. So the degree of this polynomial is 3. Degree is 3. So that means every time you find a successful 0, like we did, you're going to knock it down by 1 power. So it started as a degree 3. That's why when I found 1 0, I kind of pulled one of the powers away from the 3. So there's only a second power left. That's how I knew that I only really needed to find 1, because once I found 1 0, what remained would be a quadratic, and I can just either factor it or use the quadratic formula. But I don't think this guy factors. Does not factor. So I'll have to use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac over 2a. Okay, and I'll substitute what I know in. Negative b is 3, plus or minus the square root of b squared, that's 3 squared, minus 4 times a, which is 1, times c, which is negative 6, over 2 times a, which is 1. Alright, we'll simplify this. And I can't forget, too, that this guy's going to give me another solution. If I set him equal to 0, I got negative 1. So I can't forget to put that in my answer. That's the easy one. But the other two are going to come from this quadratic formula here when I simplify it. 3 squared is 9. Negative 4 times 1 times negative 6 is positive 24 over 2. Okay, let's see. Does this simplify very much? Negative 3 plus or minus, let's see, square root of 9 plus 24 is 33. Is that right? Yeah, over 2. And I think the square root of 33 doesn't simplify, so I think that's as good as it gets right there. There's our three solutions. X equals negative 1. And then this guy when it's a plus instead of a minus, and then when it's a minus instead of a plus. Whew. So it's kind of a lot of work, and obviously that was only a third power, so if it was a fourth power, fifth power, it'd be a lot harder. Alright, and then this next objective, it says solve polynomial equations, which sounds like it's something totally different. We're actually going to use the exact same directions as the previous problem. Same, or strategy, I guess I should say. Same strategy as previous problems. We're going to use the rational zeros theorem first. Let's try that. Rational zeros theorem. Okay. So it says that it's P over Q. Okay, and P should divide into the constant term, which in this case is 13. That's kind of nice because actually not a lot divides into 13, right? 1, negative 1, 13, negative 13. So that's not so bad. And then Q must divide into the leading coefficient, which is 1. 1, so this guy's coefficient. But the only thing, like we've seen before, that it divides into 1 is 1 or negative 1. So when I kind of combine these, the combinations of those P's over those Q's, there's not a whole lot of options. Combos. Let's see, it'll be plus or minus 1 over plus or minus 1. That'd be this over this. And then plus or minus 13 over plus or minus 1. So not a whole lot. And then let me simplify that. What are all the possibilities of those guys? When I let the plus or minus become a plus or a negative or whatever, simplify. Well, the first one, the 1 over 1, the only thing that can be is either a 1 or a negative 1. No matter which of those is positive, which of those is negative. The second guy similarly can only be a 13 or a negative 13, and that's it. So that's kind of nice. That's not a lot of possibilities. So, I mean, the worst that can happen is I have to use synthetic division 4 times until I get the right guy. But that's not that bad. It could have been worse, I think, for sure. So now I'm gonna try one of those guys. I'll try, like I said, I'm boring, so I always try the first one, 1. Alright, and now I forgot what the coefficients were of f of x. It was 1, negative 6, 22, let's see, 1, negative 6, 22, and then what? Negative 30 and 13, okay. 13, alright. And just be careful, because, you know, when you're doing synthetic division, if you make any little mistake, that's going to affect the whole rest of the synthetic division. So for example, this might be an actual 0, but if you make a mistake, your remainder won't be 0, because you made a mistake. So you'll miss the 0 that was actually right. So just try to be really careful, so you don't miss a 0. Or else, I guess once in a while, you might make a mistake, and you think the remainder is 0 when it's not really. So you think you found a 0, but you actually didn't. Alright, we're going to bring down the 1, multiply by the guy outside. We'll add that with the guy above it. Multiply, add, I think is that 17? Yeah. Multiply, add, multiply. Oh, look at that. Look how lucky we got. 0 remainder. Man, the first try was the right one. Yay! Okay, that means x equals 1 is a 0 or solution, I guess. You know, before in the previous problem they said find all the zeros. In this section, or sorry, this objective they're saying find all the solutions. But really it amounts to the same thing. So we found one solution, but the rest of them will come from kind of the quotient, or these numbers down here below the division bar. So x minus 1 is a factor, but the rest of it comes from these numbers here. So the very rightmost one, negative 13, must be the constant. And then from there I'm adding powers of x. So I have a x to the 1 power for 17, The next guy, negative 5, must have an x squared power. And the last guy must have a x to the third power. So that looks good. Alright, there's not really much to clean up. I guess I can just get rid of the 1 in front of the x cubed. 5x squared plus 17x. Alright, and this is where I make this kind of Hail Mary or last ditch effort. I say, man, you know what would be nice is if this cubic, because this is not a quadratic, so I can't use the quadratic formula, but it could be, it's possible that it factors using factor by grouping. Then you won't have to use synthetic division again. That would be nice. This factor by grouping, but if you try it, it won't work. No, sad. So what I have to do instead is, since I can't do factor by grouping, I can't use the quadratic formula. Obviously, this is not a quadratic, and I can't factor in any other way. I have to use synthetic division to break down this smaller one. Synthetic division to break this down. Yeah, because this problem has started with a fourth power polynomial. Now we've broken it down to a linear factor, x minus 1, and a third power polynomial. So we've knocked it down by 1 power, but we're going to have to knock it down one more time a little bit. So I guess synthetic division of x equals 1 work. Let's try negative 1, I guess. Let's see how that goes. But again, what I'm doing now is I'm not trying to break down the original one. I've already broken that one down. I'm trying to break down this new guy down here. So I'm only going to use these numbers. I'm not using the original numbers when I use synthetic division. I'm going to put those guys down here. What do we got? 1 is the coefficient of x cubed. Negative 5 is the coefficient of x squared. 17, the coefficient of x. And negative 13, the constant. So I'll bring down the 1, multiply by negative 1, add, multiply, add. This is not looking good. Multiply. Okay. Alright, those definitely do not add up to 0. Not 0. Sad. So you might, when you're doing homework or you're taking an exam or a quiz, you might have a lot of scratch paper that you're kind of doing this on, because you're not successful when you're doing synthetic division all the time. So okay, let's try 13 here. But the same numbers, because I haven't broken it down yet. Let me see, I'll bring this 1 down, multiply by 13, add, I'll get 8, multiply by 13, uh-oh, what's that? 104? Oh lord, that's not good. Let me add those guys. 121 times 13. Well, for sure this is not 13, because that was what I would need to get a 0 here. So this is not 0. Alright. Let's try negative 13. That's my... Well, let me see. I'll say right now that that's my last resort, but there's another option. I'll get back to that once we're done with this one. Bring down this 1, multiply, add, what's that, negative 18? Multiply, uh-oh. Alright, so I got 234, wow. This is not looking good. I think when you start to get really big, crazy numbers, that's not a good sign. And let me add these guys together, let's see, oh lord. 251, I'm pretty sure when I multiply that by negative 13, it's not going to add up with negative 13 to give me 0. Not 0. But oh well, let's try it anyway. 251 times negative 13 is, negative 3,263. For sure when I add that with negative 13, I'm not going to get 0. Okay, so I'm kind of glad this happened, because notice I've tried the other 3 numbers that were the result of the rational zeros theorem. So it's like, well, I've run out, so now what do I do? Well, the answer now is, it could be that x equals 1 is a 0 again. Maybe x equals 1 is a 0 again. That would just mean it has multiplicity 2, if you kind of remember us talking about multiplicity 2. Because yeah, that was the one that was a success to begin with, right? X is a 0 or a solution. But it's possible that it's the same guy as a solution twice. So I'm going to try 1 into the smaller polynomial we've been working with here. What were the coefficients? 1, negative 5, 17, negative 13. 17, 13. Negative 13? Yeah. Alright, so let's bring down the first guy, multiply by the guy outside. 1 times 1 is 1. If I add 1 and negative 5, I get negative 4. Multiply, 1 times negative 4 is negative 4. This is looking good. 17 and negative 4 makes 13. That's pretty familiar. 1 times 13 is 13. If I add those together, I get 0. So there we have it. Okay. So it looks like that means x equals 1 is a 0 twice. So f of x is, we already had x minus 1 once, and now we have it again, because it was a 0 again. And then what's left down here is going to give me the remainder of my polynomial, x squared minus 4x plus 13. Now that it's quadratic, I should either be able to factor it, or I can use the quadratic formula. I think that guy does not factor though, so we're going to have to use the quadratic formula. The first two factors, we're going to get x equals 1 if we solve those. They didn't ask, but if it matters, you have multiplicity 2, because it occurred twice. But this guy, though, we're going to have to use the quadratic formula. Let's see, x equals negative b. Negative b is negative 4, which is positive 4. Plus or minus the square root of b squared. B is negative 4 squared minus 4 times a, which is 1, times c, which is 13. All over 2 times a, which is 1. So let's see, we got 4 plus or minus the square root of, let's see, negative 4 squared is positive 16. 4 times 1 times 13 is, let's see, negative 52. That's not a good sign, huh? So 4 plus or minus the square root of, that's going to give me a negative inside the root. A negative, it actually doesn't matter, negative something. Whatever, those are imaginary solutions, because you can't have a negative in the root. So no solutions coming from this part. So that means there's only one solution. X equals 1. We have found that guy twice. Oh man, that just seems like we wasted a lot of time, huh? Oh well, it happens. Alright. So let's try this next one. This one should be a little easier, because notice the degree is 3. The last one, the degree was 4, so we had to break it down twice. This one's a lot less work. So let's go for it. We'll do the rational zeros theorem first. Rational zeros theorem. So if p over q is a 0 of this guy, p has to divide into the constant term, which is 12. Ooh, I don't like that, because 12 has a lot of divisors. And q has to divide into the leading coefficient, which is 1, so that's not too bad. So 12, okay, what divides into 12? 1 and negative 1, 2 and negative 2, 3 and negative 3, 4 and negative 4, 6 and negative 6, 12 and negative 12. But at least q, there's only one option, plus or minus 1. Okay, what are all the possible combinations of those guys? Combos. Well, it's pretty much each of the p's that we found over plus or minus 1. Plus or minus 1 over plus or minus 1. Plus or minus 2 over plus or minus 1. Plus or minus 3 over plus or minus 1. Plus or minus 4 over plus or minus 1. Plus or minus 6 over plus or minus 1. Plus or minus 12 over plus or minus 1. Alright, now we'll simplify each of those guys. Think about what those could possibly be. The first guy can only be 1 or negative 1. The second guy can only be 2 or negative 2. The third guy can only be 3 or negative 3. The fourth guy can only be 4 or negative 4. The fifth guy can only be 6 or negative 6. And the very last one can only be 12 or negative 12. So, I mean, that's quite a list, I guess. That's kind of a lot to choose from. But at least they're all whole numbers, because a lot of times you get fractions on these. Alright, now our job is to try to guess one of those. Like I said, it's up to you. There's no wrong guess. It's not like you should have an instinct about it or anything like that. Later on, we'll talk a little bit about how you can maybe narrow it down or help yourself guess better. But I'm just going to, like I said, go from left to right. I'm starting with 1, and I'm trying to divide into, let's see, the original guy was x cubed, so a coefficient of x, minus 2x squared, so that's his coefficient, minus 11x plus 12. Okay, so those are the numbers I want to see in my synthetic division. I'm guessing x equals 1, just in case later on you come back and say, what the hell, why is there a 1 outside that, or inside that division box thing? Bring down this guy. That 1 multiplied by the 1 makes 1. If I add 1 and negative 2, I get negative 1. Multiply by the 1 outside, that's negative 1. Are you kidding me? We're going to get really lucky right now. If I add those guys together, I get negative 12 times the 1 outside is negative 12. Oh, hell yeah. Man, we got lucky. X equals 1 is a 0. Yay! See, I think that's why I always start from 1 and negative 1, because they're always going to be part of the candidates here. And a lot of times they work. I think the reason is because if 1 and -1 aren't zeros, if it's bigger numbers, then your polynomial ends up getting really big and ugly with a lot of big numbers. 1 and -1 kind of contain it and keep it small. Okay, x equals 1 is a 0. So the function we were given can be broken down to x minus 1 times, okay. And then these guys, other than the remainder, we're ignoring that. These are the coefficients that we want. So 1x squared minus 1x minus 12. And you know what's awesome is that guy actually factors. Well, first of all, that's quadratic, so I should not have to do synthetic division again. Quadratic. Although if you wanted to, you could use synthetic division to break that down if you didn't like factoring or using the quadratic formula. So no need for more synthetic division. Because at this point I should be able to finish the problem by either factoring or using the quadratic formula. But this guy actually factors. It's x minus 4x plus 3. That x squared minus 1x minus 12. So since the original problem said solve this thing equals 0, basically I have this factored form. I'm going to set this equal to 0 and solve for x. Each of these factors can be set equal to 0, and then I can find all my solutions. X minus 1 equals 0, x minus 4 equals 0, x plus 3 equals 0. The first guy, if I add 1 to both sides, I get 1, so there's one solution. If I add 4 to both sides to the second one, I get 4, there's another solution. And if I subtract 3 from both sides in the third one, I get -3 as a solution. So there are your 3 solutions. Each of them, not that they asked, but each of them has multiplicity 1 because you don't see any of those occurring in more than one factor at the same time. Ah, so that's tough. Okay. So where are we now? Factors. Okay. So the rest of the section, and this is a really long section, I'm sorry. Chapter 3 is very dense. It's got a lot of material. We still have 2 objectives left. Sorry, I'm kind of checking it out. Yeah, but the rest of it's more for... Okay, honestly, what happens in real life is not all polynomials have real solutions. Kind of like we saw above. I think it was 2 examples ago we saw that you could have imaginary numbers as solutions. So the objective 4 and objective 5 kind of go deeper into that. What if you have imaginary solutions? Is there any kind of tricks you can use to find them? Or, yeah, is there any way to make it easier? Things like that. But let's see. First things first. In objective 4, they have first the linear factorization theorem. What does it say? If you have a polynomial of degree n, okay, then blah blah blah. Okay. Then our complex numbers. So complex numbers we saw, those are just numbers of the form a plus bi. That was the very first section we covered in this class. Possibly, real and not necessarily distinct. Okay, but really what all that means is I think the yellow highlighted part that we're going to highlight is more important. An nth degree polynomial can be expressed as the product of a non-zero constant and n linear factors, where each linear factor has a leading coefficient of 1. So in other words, a polynomial of degree n will have n factors. Will have n zeros. That's pretty much what this says. A polynomial of degree n will have n, I'm going to say first linear factors. So n zeros, although I'm going to say sometimes repeated. Like we saw, I think, in a previous problem, a couple examples ago, we saw x equals 1 was a factor twice. We're counting that as 2 different zeros because it occurred twice. So it's kind of nice. So if you look back at the problems we did before, if you look at the degree of the original polynomial, that's the number of solutions we found. If it was a 3rd degree, we should have found 3 solutions. If it was a 4th degree, we should have found 4, on and on. Although they could be, as I said, they could be complex numbers, which means, they could have an imaginary portion. So just kind of like think about the degree of your polynomial is the number of solutions you should have, but you're not really sure yet how many of them are real, how many are imaginary. So, okay, let's see if that'll help us solve this first one. 4a says, find a 3rd degree polynomial function, f of x, with real coefficients that has -3 and I as zeros, such that f of 1 equals 3. Oh my god, that sounds crazy. But actually, that one, we're going to need this other theorem. I'm sorry. I put it over here and I kind of forgot about it. The conjugate zeros theorem. Okay, what does it say? If a plus bi, which, okay, that's a complex number, I being imaginary, If a plus bi is a root of a polynomial function with real coefficients, then the complex conjugate, remember we talked about conjugates before, a minus bi is also a root of the polynomial. So here, in this example, for a, that means, let me see, I'm going to write it out just to be careful. According, so it makes sense later, when you read it later, to the complex conjugate, alright, what does it say? The conjugate roots theorem, I think is what it was called. Roots theorem. Since this problem tells me that I is a 0, because it said that here, its conjugate, conjugate, negative I is also a 0. So they gave me, you know, specifically two different zeros, x equals 3 and x equals I. But now I have a third 0 that they didn't even tell me, but it just, according to the complex conjugate conjugate roots theorem, I have kind of a freebie root here that they didn't even mention. So and that's, if you're wondering what the heck, why is I and negative I conjugates? Well, I, if you think about it, that's the same as 0 plus 1i, okay? If you're trying to write it as a plus bi type of thing, I doesn't have a real portion, but if you put a 0 there, it kind of looks like it's real. So it's conjugate. I would find it by just changing the sign in between those guys, 0 minus 1i, which is really just negative I. So that's why negative I is the conjugate. So, okay, according to that complex conjugate roots theorem, negative I is also a root. So we have 3 roots. 2 were given and 1 I had to find out using that theorem. 3, okay, I should say zeros. X equals negative 3, x equals I, and x equals negative I. But since they said in the beginning that this is a third degree polynomial, there should only be 3 solutions. That's what they said. So f of x, the function that we're looking for, should be some kind of coefficient. I'm not sure what it is. A, I'm going to call it, times x minus each of the zeros. They should each have their own factor. See, I guess that's the only tricky thing about this, is you don't really know what the coefficient in the front is. You know what each of the little factors are. I just say x minus the first 0, x minus the second 0, x minus the third 0. But we need to find a, I guess, is the idea. But maybe I'll clean this up a little bit. F of x equals, alright, a, I don't know what that is, but x minus negative 3 is the same as x plus 3. And then we have x minus I, and then x minus negative I is x plus I. Alright, so now I'm supposed to find a, because I want to know what this polynomial is. If I don't know what a is, I don't really know this guy very well. But the only thing we haven't used yet is the fact that they said f of 1 equals 8. F of 1 equals 8. So in other words, when x equals 1, f of x equals 8. So I think if I replace, you know, for example, in here, if I replace x with 1 and f of x with 8, I should be able to solve for a. So that's my idea. I'm going to replace x with 1 and f of x with 8. Then the only thing I don't know should be a, so I should be able to solve for it. And solve for a. Alright, let's go ahead and do that. F of x, okay. F of x is now an 8 equals a, which is what I don't know, times x plus 3, but we said we're replacing x with 1, and then x minus I, but x is 1 minus I, and x plus I, but we said x is 1 again. Okay, so I want to solve for a, but maybe I'll multiply this out over here on the right side. I'll see what that is. 8 equals, okay, a. Well, 1 plus 3 is 4, so I got that here. And then I think I'm going to FOIL this out. I think when you have conjugates like this, notice 1 minus I and 1 plus I. Usually they multiply out really well, like we've seen in the very first section in this class, when we reviewed conjugates. So if I FOIL that out, I get 1 plus I minus I squared equals a times 4. Let's see, and the i's in the middle, I minus I cancel, so I'm just left with 1 minus, but remember I squared is negative 1. I squared is negative 1, so I replace that guy. A times 4, okay, then it's 1 minus negative 1, which is 2. So really this just says 8 equals 8a. So if I solve for a, that must mean that a is 1. Alright. Now I can finally fill that in, because we said f of x is a times x minus 3, x minus I, x plus I, or some crap like that. Oh wait, was it plus 3 or minus 3? Plus 3. But now that we know a, we can fill it in. F of x equals a, which is 1, times x plus 3, x minus I, x plus I. There's my answer. Although you could remove that 1, right? Because any 1 as a coefficient is kind of unnecessary. But I didn't know it was going to be a 1. I had to do all the math to figure it out. Sometimes a is 1, sometimes a is -1, sometimes it's 2. It just depends on the problem. So there it is. That's the final answer. Whew. It's kind of a lot of work, huh? I feel like somehow it's less work, or less thinking than the previous example, though. The previous objective. Let's try this next one. It should be similar. It says, find a 4th degree polynomial function with real coefficients, okay, such that I is a 0. Let's see, so zeros are I, and they said also 3I. And then this last part is going to help us find a. Fine. So that we'll use later. But okay, since it's a 4th degree polynomial, they said I should have 4 zeros. There should be 4 zeros, but they only gave me 2. But according to that conjugate's roots theorem, conjugate roots theorem, if I is a root, then negative I should also be a root. If 3i is a root, then negative 3i should be a root. So we really have 4 zeros here. They gave us I and 3i, but as a freebie we got negative I and negative 3i according to the complex conjugate roots theorem. So the function that I'm given, or that they're talking about, should be a, some kind of coefficient, times x minus the first root, x minus the second root, x minus the third root, and x minus the 4th and final root. And like I said, I know there are 4 roots because it's a 4th degree. Remember this theorem over here, the linear factorization theorem, basically tells us that the degree of your polynomial is the number of roots you should have. So once I find 4 roots for this example, I shouldn't go looking for any more. The first one was I, and then I also have negative I. I had a 3i, and then I also had a negative 3i. Alright, let me try to clean that up a little bit. F of x equals a times x minus I, x plus I, and then x minus 3i, x plus 3i. Alright, so my last step is to find a, but I can do that using that last fact that we haven't used yet. Find a using the fact that f of -1 is 20. Because that should mean that I can replace x with -1. Let's see, x equals, and f of x with 20, because f of x is the same as the y value. So here I'm going to put a 20, and where all the x's are, I'm going to put -1. I got to be careful though, because it's negative. So it's -1 minus I, because there was an x there, and then -1 plus I, -1 minus 3i, -1 plus 3i. Alright, and just like we did before, I'm going to have to FOIL these out. But like we kind of mentioned, if you multiply the complex or the conjugates together, like these guys are conjugates, multiply them and multiply them first. Do that first, and then your life will be a lot easier. So I'm going to FOIL that out, the -1 minus I and -1 plus I. See, -1 times -1 is +1. And -1 times I is negative I. Negative I times -1 is positive I. Negative I times positive I is negative I squared. Alright, and maybe I'll just keep working with that until I get it down to as simple as it can be. That's 1, and then the i's cancel, minus, but I squared is -1, like we said before. So it's 20 equals a times 1 minus -1 is 2. So we simplified as much as we can what's in the first parentheses. Now we'll try the second parentheses. Let's see, if I FOIL this guy out, you have a -1 times a -1, that's +1. -1 times positive 3i is negative 3i. Negative 3i times -1 is positive 3i. And lastly, negative 3i times positive 3i would be negative 9i squared. Alright, then those 3 i's cancel because one's positive, one's negative. We're just left with the 1 minus, let's see, 9 times I squared is negative 1. Remember that. That's pretty important. So that looks like, pretty much it's 1 plus 9, because the negative and the negative make a positive. So 1 plus 9 is 10, clearly. And there we go. Oh my gosh, we're going to get the same A as we did last time. I feel like I just wasted a bunch of time. 20 equals A times 20, so 20A. Oh my gosh, really? So A is 1 again? Son of a gun. Well, all that work because we don't really know if A is going to be 1. Blah, 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 blah. Alright, so our function that we wanted was A, okay, which is 1, times x minus I, x plus I, x minus 3I, x plus 3I. There it is. Oh my gosh, that's a lot of work. And of course, now that you've set it up, you can drop the 1, I'd say. But whatever. If you left the 1, I wouldn't mark you down, that's for sure. Oh Lord, okay. This is the last objective in this section, which thank God, because this is a lot of work. And this one, what this one does is Descartes' rule of signs is supposed to kind of narrow down, like, you know, when we did the rational zeros theorem a couple problems back, sometimes you end up with a lot of possibilities, so you might have to do synthetic division a lot of times to try to get the right guy. So this one's useful when you have a lot of possibilities. It kind of narrows it down or helps you guess. Well, maybe I'll try to guess all the negative numbers first, because I know they're more likely. Or, oh, I don't think negative numbers are very likely. I'm going to try the positive numbers. That's kind of the idea behind this guy. The only thing is this Descartes' rule of signs is very hard to wrap your mind around. It takes a couple tries, you know, you try a few examples, and then it kind of makes sense. Let's see, let's just read it once, and then we'll try an example with it. Let p of x, which is a polynomial written in descending order, be a polynomial function with real coefficients and a non-zero constant term. The number of positive real zeros of that function is either the same as the number of variations in sign. So variations in sign means, you know, if you're looking from left to right, does it go positive, negative, positive, negative? You know, those are variations in sign, because you have a positive and then a negative and then, you know, on and on and on. Or it could be, this is confusing, less than the number of variations of sign in that function by a positive even integer. So it really, I'm just going to kind of paraphrase that. That means you're going to keep subtracting 2 from that number until you get 0. That's what we'll do. Okay, and I think that doesn't make a whole lot of sense right now, but once we do an example, it'll make more sense. And then the second example will really, I'll hopefully drill it in. And then the number of negative real zeros in p of x is either the same as the number of variations in sign of p of negative x. So this isn't the regular polynomial, this is me having to replace x with negative x. Or less than the number of variations of sign in p of negative x by a positive even integer. So that part is kind of the same as what we wrote above. Keep subtracting 2. Same thing. 2 from that number until 0. Alright, that doesn't make a whole lot of sense, but let me try to paraphrase it when we do this example down here. I have to think the number of positive real zeros. Okay. That's what we get from above in Descartes' rule of signs between 1 and 2. That's what that's telling us up there. Okay. If I count the number of variations in sign from left to right, there are how many variations in sign? Well, it goes positive to negative. Okay, that's one variation in sign. So I'm going to mark that down. And then from negative to positive, that's another variation in sign. From positive to negative again, that's another variation in sign. And then from a negative to a positive, that's 4 variations in signs. So there are 4 variations in sign. So that means that it is possible that there are 4 positive real zeros in this polynomial. So that's like your first step, kind of right there. And then step 2 was saying something crazy, but then I said, just keep subtracting 2 from that number until you get to 0. So I'll subtract 2 from that guy. Let's see. 4 minus 2 would be 2. So that's a possibility. And I'm going to subtract 2 again, because I'm supposed to do it until I get to 0. There we go. So those are the possibilities. It could be 4, it could be 2, it could be 0. So that's kind of the idea here. Okay, so there are either 4, 2, or 0 positive real zeros. Alright, and I feel like that doesn't feel like it really narrows it down, you know? There's 4, okay, that's a lot. Or there could be 2, okay, that's not that many. Or there could be none. Well, great, that doesn't really help me. But I guess now the next thing is we're going to figure out how many negative real zeros there are. And let's say if there's way more or way less, then we'll know we want to try to guess the type that there might be more of, you know, when we do synthetic division. Okay, now we'll do steps 3 and 4 will tell us how many possible negative real zeros there are. Number of negative real zeros. So obviously this, when you're looking at this, the only way this would be really helpful or not a waste of your time is if you do the rational zeros theorem, you know, where you do p over q, p divides into this, q divides into that. But you're having a really hard time, I mean, you end up with a lot of possibilities, and you don't want to do synthetic division that many times to narrow it down. This sort of narrows it down a little bit to where it'll make it easier. That's the only time this would be useful. But steps 3 and 4 above say that the number of negative real zeros involve you having to calculate what p of negative x is. So for this example, I'm going to have to substitute negative x into this. Substitute negative x in. That'll help me with steps 3 and 4. So I'm going to say I'm replacing the x here with the negative x. The next x also with a negative x. Sorry, I'm going to be running into the next problem, but that's okay. The next guy with a negative x. The next guy with a negative x. And then obviously the constant term doesn't have an x, so that doesn't make sense. So let's simplify that. Any even power is going to make the negative disappear. But this odd power keeps the negative, but that negative along with the negative in front makes it positive. The next term makes the negative disappear because it's a square. A square and a negative cancels it out. These two negatives make a positive. X plus 120. Okay. So that's p of negative x, or f of negative x, whatever the function's called. Notice though that now all the terms are positive. So there are no or 0 variations in sign of p of negative x. So that means there are 0 negative real zeros. And then if that was a number other than 0, you know, if I got, like in the last one I got 4, then I would keep subtracting 2 until I got 0. But that's useless because 0 minus 0 becomes a negative. There's no way to have a negative number of something. So that's kind of that one would actually narrow it down for you if you were doing this problem. Because, you know, you do the rational zeros theorem, you have a bunch of possibilities. It's possible there are 4, 2, or no positive real zeros, but there are definitely no negative real zeros. So if you were to go back to a previous problem where we actually did the rational zeros theorem, let's see. Like objective, what is it up here? Objective 3. So once I wrote them all out, like these guys right here say, then I can just throw away the negatives because we found out just now that there are no negative real zeros. It's not possible. So you might as well only try the positives. You know, in this example, that wouldn't really help because in that case, when we did the rational zeros theorem, there were only 4 possibilities anyway. That wasn't really worth it. But if there's a lot of possibilities, it's probably worth trying to narrow it down. Let's try that one more time. This is very, very complicated stuff. Now in 5b, we're determining the possible numbers of positive and negative real zeros of a new function. Alright, so we're going to say the first step is how many sign changes are there in f of x? F of x has actually no sign changes, or 0 sign changes, because every term is positive. It's not like it goes positive to negative, negative to positive, anything like that. So there are 0 positive real zeros. Alright, that would have definitely narrowed it down if we were doing the rational zeros theorem. Because if we came up with a big list of numbers, now I can just throw away all the positive ones because I know none of them are going to work. And then step 2 is kind of out, because now I'm supposed to keep subtracting 2 from this guy until I get to 0, but it already is 0, so that's kind of a waste. But step 3 wants me to put a negative in for x, and then count the number of sign changes for that guy. Negative x cubed plus 2 times negative x squared plus 5 times negative x plus 4. Let's see, what do we get there? That's a negative x cubed plus 2x squared minus 5x plus 4. Now I'm supposed to count the number of sign changes. Let's see, I have one from here to here, because it goes from negative to positive. And another one from here to here, another one from here to here. 3 sign changes. So that's a possible number of negative real zeros. Step 4 says now we're going to subtract 2 until we get to 0. Oh, now we're at a negative. That doesn't count. So it's either going to be 3 or 1 negative real zero. Because we started with 3, we subtracted 2 from that, we got a 1. We tried to subtract 2 again, but that was the end of it. So that means there are either 3 or none, well, none, I should say 0, negative real zeros. Real zeros. Alright, so that means if I were to do the rational zeros theorem and I had a bunch of numbers to try synthetic division on, I would definitely throw away all the positives, because right here it says no positive answers are going to work. Either 3 or 1 of the negatives is going to work. And if you're kind of savvy, you're thinking, wait, this is a polynomial that's a third degree, right? Here he is, third degree. So it's supposed to have 3 zeros. If none of them are positive, then you would think all 3 of them would be negative, right? That would make sense. But I guess the idea is some of them can be imaginary. So it could be that 1 is a negative real zero, but the other 2 are imaginary guys. So that's kind of the idea behind the subtracting 2 thing. And yeah, that's actually why you subtract 2, because that's like, if you lose one of the zeros to an imaginary number, or a complex number, you're actually losing 2 zeros to a complex number, because remember, they come in conjugate pairs. Because if a plus bi is a 0, so is a minus bi. So this stuff's complicated, but we'll kind of go over it again, as we go over more complicated stuff in the coming sections. Oh, sorry for such a long video, but it's a lot of material packed into one section. The next section should be a little better. Okay, it'll be fun. I'll see you in the next